class in here for us?
Yes.
A big one?
Medium size.
Is it
More than this.
It seems cold to me.
It's colder though.
All right.
Review day.
Huh?
Review day?
Yeah, I'll take your questions. This Friday's the test, right?
Yes. Yep.
Got that one right. All right. One of the questions I used to get is, how many questions on the test? Well, there's usually 4 major topics, but, you know, when you say questions, there's multiple parts to each one, so that's what I can tell you. Have I made it out yet? No. So, it's another one I can check out. Anyway, go ahead. With your questions. I have new material, but go ahead.
I have kind of a question. It's about the freeze, I think it is. It was basically, the question is, if you're given like 2 antennas,
Uh-huh.
and you have a radius, and you're given one angle for, like, it's for the phone. What is
How
it?
about you set it up for me?
Well, it's not really a problem. It's more of a question about, let's see.
How about if we put something on the board
Sure,
and look at
sure.
the picture?
Sure.
All right, this will be the antenna transmitter. How's that?
Yes.
All right. And so it's gonna have so much power it's gonna transmit. It has a gain of the transmitter. And gain can be a function of angle. And we're gonna come out here, and here's the radial distance, here's a second antenna. And this is the receiver. And of course, this is a gain. This is the gain of the transmitter, gain of the receiver. So go ahead and ask your question.
It's a quick question. It's if you're given one angle, like if they're not set up for maximum power. if
All right,
you're
what
given
you're
one-
trying to say is if you're given this information,
Okay, is there a way to calculate the angle for the other one, or does that have to be given?
well, you have to know something about the geometry. I mean, if this antenna is vertically upright, right? And the gain is with respect to an off angle, you might as well call that alpha. Then yeah, I mean, but you have to give it enough information, you can deduce it. Now, if you know this angle, right? And if this is a right angle, by definition, you know that angle too. I mean, if you think about, what do you know? Opposite interior angles are equal, so that angle equals that angle, if they're at 90 degrees. Follow me?
Okay, yes.
But it's just basic geometry from there.
Okay, just wondering, that's not a question in the book like that, so.
You got, I mean, do you have a problem that it's related to, or Jacob, you have anything for me?
I do not have homework pulled up. Do you pull it up right now?
I've got all of them pulled up, yeah.
Don't
Okay, for
push.
13, can you
Problem.
tell them the one where it's like the blocks diagram, like find the frequency? I think it's number 2.
Number 2,
Oh, that's right.
determine the maximum ambiguous range,
Yeah,
RU.
range and the.
Yeah, you can do that.
Okay, you're gonna have to give me some.
I'll just show you, it's kind of like awesome.
You don't have to show me, just give me the info so I can
Just
put it on.
determine the maximum ambiguous range, RU, and the range.
Unambiguous range, right?
Yeah, is that what I'm saying?
Non-ambiguous or unambiguous.
Range RU and the range resolution delta R for the baseband radar pulse shown below.
All right,
Uh,
so now just tell me this. It's on for a certain length of time. What is this time?
20 microseconds.
20 microseconds, and then it repeats over some interval.
Mhm.
What is this time?
That's 200 microseconds.
200
Oh, it's a little, yeah, roughly.
microseconds. Not nano.
Yeah.
200 nano. It can't be less than the first. 200 nanoseconds is 0.2 microseconds, right?
Like 180.
Is that right?
Yes, 200 microseconds.
Yeah,
Okay.
it's a little
And
longer.
so they want first the maximum unambiguous range, right? That's the first one.
Mhm.
So the whole deal with this is, what does that mean? Well, when you send a radar signal, and there's a target here, at some range, the total time it takes to travel, the way if you go out and come back, it goes over a distance in 2R, right? Is that right?
Is it-
Wasn't supposed to until like 5.
My wife literally asked
Well-
me if I wanted the umbrella.
Somebody,
Said no.
Auburn weather, I'll tell you what. The weather forecasters, they try their best, but it's still a coin flip sometimes. You look up and it's getting dark, it's gonna rain. Anyway, it moves 2R. Do you agree with that?
Yes.
Now, the velocity is the speed of light, correct? So if you divide that by c, now you get the time, the delta t, right? Now, here's the deal with maximum unambiguous range. Before you send the second pulse, the first pulse has to return, all right, the echo. So what you do is say that this is actually called a PRI. That will tell you how far away you can be to a target for it to be unambiguous. Now, the fact is, well, what if there's a target further out? Well, then if a target reflects further out and its signal is above a threshold, then there is an ambiguous target, all right? But usually what they do is set the ambiguous range up, or they set this time such that the largest target possible, there's a lot more to this. The signal reflected from it will not be enough to cause a triggering event where you'll say, oh, there's a target. It's going to be too small. And there's other ways. So anyway, if you say this, that means that that would be T, or the PRI, the pulse repetition interval. And therefore, that range R, we call the maximum unambiguous range, would be equal to C tau, or C times T over 2, or C times the PRI over 2. So the PRI was 200 nanoseconds, or 200 microseconds, right? So this would be, well, C is 3 times 10 to the 8th over 2, and the PRI is going to be 200 microseconds, or 2 times 10 to the minus 4th seconds, right? So if you look at that, the 2's cancel, and I have 3 times 10 to the 4th meters, or 30 kilometers. And by the way, 30 kilometers for an airport radar is reasonable. Do you agree with that? A kilometer is 1,000 meters, right? 10 to the minus 4, 10 to the 8th would be 10 to the 4th, right?
Yeah.
2's cancel, you get 3 times 10 to the 4th. Do y'all agree with that?
Yes, sir.
All right, so that's the maximum unambiguous range. In a similar way, the delta R, the range resolution, if you just think about this, as a pulse is coming down of a certain width, as it's hitting, it's reflecting, right? So think of a time T, set it equal to 0 when the pulse hits there. In other words, this is a target. Take a snapshot of time, and this is what the pulse looks like just as it's hitting it in time, right here, all right? So it's got a width tau. Now, this is a T equals 0. A little bit later, when the pulse is coming, this is the part of the pulse that's hitting, and this is going to be the part of the pulse that's reflecting. Do y'all see that? That makes sense here? This part's going in, this one's reflecting off. I can't draw this real well, but just follow me. You know, the whole pulse was moving, then it hits, then part of it starts reflecting. Well, the thing about it is, the maximum unambiguous range will be that tau, if you think about it. How long does it have to be, what does the spacing have to be between this and the next target? What does the spacing have to be so the two don't overlap? And if you take a look at this delta R, this is C times T over 2, or C times PRI over 2. This will be similar, C tau over 2. So if you make delta R here, you can go through this mental exercise. If you let that be C tau over 2 or less or closer, you can't tell when the first target reflection started and the second target reflection started, all right? They'll overlap. What'll happen is, if you just make them, if you take a look at this, as this pulse is going in there, call this, I'm trying to do this without, here's the primary pulse. I guess I'm trying to think of the best way to show you guys this. If this is target 1, and here's target 2, if the primary pulse is here, right, it's moving this way, there is no reflected pulse yet. If the primary pulse is here, there's going to be reflected pulse the same length here, but here's the primary pulse, right? This is reflected. Now keep going. When the primary pulse is here, then the reflected pulse is here, but then you get a reflection, right, off of here. You all follow me? But if this is C tau over 2, now the two overlap, and you just get a much longer primary pulse. You go ahead and mess with this. I wish I had a simulation, but you can find it on YouTube. Just look up, I think you can at least, look up radar range resolution simulation. They'll show you this, where you got one pulse coming in, you got 2 targets, right? Pulse hits the first one, starts reflecting back, still hasn't hit. Hits the second one, starts reflecting back. If you take C tau, that has to be twice the distance, because before the pulse stops on the first one, the second one can't have a reflection back on the first place with the first one. This isn't coming out real well, but do y'all understand what I'm saying?
Yes.
And it's one of those things you can look at a simulation, it's pretty cool. And I'll just level with you. Range resolution is kind of common sense, and so is the maximum unambiguous range. If you just think about it, it really isn't. There's nothing here that's magical. It's like, that makes absolute sense. Think about the analogy with sound, for instance. It doesn't have to be electromagnetics. For sound, you wouldn't use C, you'd use the velocity of sound in the medium. What is the velocity of sound in meters per second at sea level?
343.
343, is it?
Yes.
About 340 meters per second. Put that in perspective, about 1,000 feet per second, roughly.
Close.
All right,
About 700 something. 700 feet per second.
so how many of you have shot a 22 rifle before? 22 long rifle goes about 12 to 1,300 feet per second, right? It is supersonic, so you'll hear a sonic blast. A 45 is subsonic, right? Now, that gives you sort of perspective on that, where you know, when you talk about the speed of sound, it's about as fast as a slow bullet, if that makes sense. The speed of light, to give perspective on, I don't know if you guys, it used to be that they try to give the engineers, they try to give scientists, people that work in nature, geophysicists, a reasonable idea of what they're talking about when they talk about any kind of velocities or strengths or power. So, well, the speed of light, here's how fast it is. In 1 second, it will go all the way around the Earth 7 times. All right, I mean, grasp that. In an instant, it's 7 times around the Earth. That's virtually instantaneous to me, but not really. All right? There's something that is it's so fast you can't actually measure it, but it does occur, which is bizarre to me. I don't know how this happens. Do you know what entanglement is, anybody? Quantum entanglement. Have you heard of this? Remember this, because some of you are going to end up, you're going to have to deal with this. You're engineers, you're going to have to. Quantum entanglement was something long ago Einstein ran into and some of these guys. What it is, when two particles properties at the, I guess, subatomic level, they're called spin, are entangled. You remember back when you had whatever it was, physics or chemistry, somewhere down the line you had something to talk about electron spins, right? Well, there are things that happen with photons and electrons. An electron can basically be jacked up in energy, and when it falls, it gives off a photon, right? But they can also give off 2 photons. Those photons, as my understanding, are created by a single energy jump, are entangled. They have I guess spins and other, they have some, photons don't have spin, they have a fundamental property that is entangled and it's measurable. So I'm not a physicist, and I don't know how to explain this any better than I'm doing. But I do know one thing about subatomic physics. Even the physicists don't have a feel for it. They just know how to measure it, and they know it's there. So they entangle two particles. Now, when a particle's entangled, in order for it to remain in that state, there has to be a very, very low temperature. It can't be in vibrational states and stuff like this, or it'll come out of it. It'll basically reveal the state it's in. And as soon as it reveals its state, the other one reveals its state. Just go with me on this. It happens. This is, to me, it sounded like pseudoscience, but they proved it. And I wish I knew more about how they proved it, because I'm always suspicious of physicists. And anyway, the Italians, I think, were the first to really get a lot of credit for this. They separated two entangled particles. I'm not sure if they were, I'm really not sure. I think they were electrons that were entangled somehow, and I don't know how they did it. And when one changed its state, the instant it changed, and they had, you know, these, they basically have clocks during universal time, so they're identical. There's no flaw with that. The other one changed instantly. If you account for the speed of light and everything, it's at least 1,000 times faster than the speed of light, according to them. You can read about this. Has anybody ever read about this? This blows me away. It's not energy. It's information. Which everybody scratches their head. It's like, well, you know, if you have sort of a string that's ultimately rigid, and you put a domino up there and tie the string to the base of the domino, got another domino here. When I knock this one down, that one will knock down if there's absolutely no stretch. Do y'all follow me? That's just information. I didn't transfer energy per se. I just gave it a tug. But still, how did it know? All right, what conveyed that? And that's the puzzle that all these people are trying to solve. And I don't know if they're ever going to solve. They know they know, I believe, they assume now it's a real thing. It just blows them away. So you've heard the term quantum computing, haven't you? Quantum computing, that thing's being thrown around, and a lot of it's baloney. Real quantum computing has to do with entangled states of things. When the state of one changes, the other changes instantaneously. In order to do real quantum, not the stuff they're throwing out there, all this nonsense. Real quantum computing is done at cryogenic temperatures with liquid helium. The biggest thing as of a year ago that they've ever solved with a real quantum computer was factoring the number 15. Now, that's 1 times 15, 3 times 5. That's it. That's how far along they've come. Because even though, and I don't understand theory, theoretically, quantum computers can solve in a probabilistic way very large problems. The reality is a real, quote, quantum computer, when a physicist talks about it can't do anything because, first of all, it's cryo temperature. Second of all, the states that they're in are there only for a second, and then they're gone. All right? Just trust me on this. When you hear it, you're going to hear it, guys. Trust me. You're going to hear all sorts of baloney. On YouTube, they're going to have, oh, this is what this is. Spin up, spin. It's baloney. Just garbage. And I'm speaking as a person that looked into this somewhat. And I've seen this kind of stuff before when they had, you guys are too young for this, but years and years ago, they had what was called high temperature, room temperature superconductors. Now, there are superconductors at liquid helium temperature. If you've ever seen, you can look this up. But there's nothing at room temperature as a superconductor. Then they had, low temperature fusion. And this is, they got a fusion reaction going at room temperature. Fusion, if you know anything about nuclear science, you know there's a thing when you take 2 helium and they fuse together and become, two hydrogen, they fuse together and become a helium, or if you take helium and rip them apart, then they become 2 hydrogens, right? Well, the energy it takes to shove 2 hydrogens together is immense. It's ridiculous. The thermal temperatures on these things are like the surface of a sun. And to take a helium nucleus with those nuclear hooks and put enough energy in that for it to split is about the same temperature. So when they say room temperature, does anybody ever go to physics classes that writes this stuff? It's an impossibility if you've ever had nuclear physics. All right? So it's like me telling you, oh, see this battery right here? I'm going to generate 100 megawatts and take that plane down. Steady state 100 megawatts for the next 50 years. If somebody told you that, you would know it's baloney. Right? I mean, I don't have to prove any, go through Maxwell's equation. You just know. Some people don't know. Trust me. Yeah.
So tau is the pulse width, right?
Tau is the on-time width right here. All right, the total pulse repetition intervals here keeps repeating itself over and over. Yeah, sorry. Back to the real one. Yeah. All right, more questions. Sorry I went off on that, but I'm thinking you're the guys that are going to be out there and have to make decisions. Is it or isn't it even plausible? And there's a lot of non-plausible stuff that's thrown around. As, oh man, this is going to work. I hear about some of the strangest stuff lately. And, this is another thing. You got to be honest with yourself. Maybe you're not qualified to make a real judgment call, but at least you'll admit you. When people just boldly say, "Oh, that's got to be true," because he said it. Dangerous, dangerous. I learned one thing long ago. Never judge any statement made by anybody based on who they are. Ever. Some of the very best people in the world make the wrong statements. Scientists do, like us. Some of the very worst make the right statements. People that are despicable. Adolf Hitler said one time that they should have a label on cigarettes that it was dangerous for your health. Now, anything from Adolf Hitler, you can't accept it. He was right about that, all right? And that's why I've learned that. I don't care who says what. I don't care who they are. I don't accept it at face value. I've got to look into it myself. So that's, sorry. I'm giving you a science lesson because I've seen some stuff on YouTube. I'm just wincing. They can't put that out there. Some young kid's going to read this and believe it. And kill himself. You got to see this stuff with, rail guns and stuff, coil guns. Here's how we make it. Kid, you don't know what you're doing. I guess they can be sued, right? They're probably liable if it's done in this country. I don't know. I know one thing. I can be sued. So I'm looking at myself and I'm reminding myself I can be sued and I don't want to be sued. All right, back to the real world. Now that I put a disclaimer. What else? Jacob, I'm surprised. You usually hit me at least one every class period between the next class. I figure you come at me with a whole
Stick any
bunch.
question on there. Listen, I can't pull them up and record the same
I'm
time.
thankful for you, all right? Because you've got something to ask me about. And I'm glad you said that because that means other people probably do and either forgot to or didn't. Another one?
Anyone have a question they want me to see them on?
So how do I ask English for
Beam width for an antenna and what pattern? Beam width is always one. Might as well do this. If you have a gain pattern, I'm going to just make one up, all right? This is a gain. I'm going to give you a gain pattern. You know what gain is. I'm going to just say gain is like 20. It's not a real gain. Times K, well, it could be. And then I'm going to make it times e to the minus magnitude of the angle times the cosine of the angle squared.
What units is that?
Huh?
What units would that be?
Put the angle in radians. It doesn't matter. You can put it in degrees if you want.
Okay.
Radians. All right. So, question I could say is, what is the beam width? So now I'd say the half power beam width. Hear me? So half power beam width, because that term gain means one thing to us as engineers. We know that the actual average power density at any distance away from a transmitting antenna will be the isotropic power, right? That's as if there's no antenna, right? Just isotropic radiation. Take total power divided by the surface of a sphere. Now you multiply it by the gain, right? Now that's the power density for a given angle. It could be a function of theta and phi. Are you with me? So if you're talking about the beam width, if we plotted that, and I'll do it linearly. If you plotted it linearly, if this is 0 and this is theta, then what you'd see is, well, e to the minus alpha, that's going to decay exponentially, and the cosine squared will be periodic, have a peak value, and cosine is 0, right? Then I would do something like this, and it would be the same in both directions. Right? Y'all agree? So the half power beam width, there's a null to null. And the null to null, you just find this one. Right? And this would be the gain. And the peak value here would be at 0, it would be 20K, right? Whatever that is, right? I didn't give you a K. So the beam width itself, you would have to find the point where it goes to half that, where it goes to 10K here, and down here, and 10K here, right? And you'd have to find that width. How would you do it? Well, you could just do it. I mean, don't make it hard, right? Just set this equal to what? 10K, right? Right? It's half the value of its peak. You follow me? Now you can find that angle. You can find half the angle. You can find this angle. Just multiply that by 2. So now what I do is I get rid, I'd say e to the minus magnitude of alpha, right? Times cosine squared of alpha is equal to simply 1/2, right? And then I'd solve that. Now, what do you notice about that? It's a transcendental equation, isn't it? I mean, try to get a closed form solution to that. I suppose you could, if you want to do a series solution on this one, you could expand this using a series solution. You might be able to do it, but this is a transcendental. Are you familiar with that term? Transcendental means there is no closed form inverse. If I give you that to find the angle that does that, there is not a single mathematical statement that can get that. I can't say theta equals, I don't think at least. Because look, if I'm solving for cosine squared of theta, I would take whatever is and stick it on the other side, then I take the inverse cosine. But this is a function of theta, right? So now what I need to do is an iterative approach. And the way you do it is this way. First, assume that's not there. Find out what value strikes that. So that would be cosine squared is 1/2. Cosine is 1 over square root of 245 degrees, right? Theta equals 45 degrees or pi over 4, right? Then you stick that in there with this, right? And see how close you get to 1/2, all right? You're going to be below 1/2, but by how much? And then what you're going to do is start creeping down the angle towards 90, because at 90, this goes away. And you see where all of a sudden are you familiar with doing this stuff at all? Haven't you done Ralph or Ralphson stuff, root shooting at all? Well, it's basically guess, see how bad the guess is, then make an adjustment, take another guess, until you get the first overshoot where all of a sudden you're getting to a larger value than you should. Instead of 1/2, if you get like 1/2 plus 1/10, then you start going back down, you iterate to the solution. I don't want to spend much time on it, but that's how you get beam width. And I hope I answered your question. It's kind of a difficult problem. If I got rid of the cosine I wanted beam width, how would you get it? Let me get rid of this. Now, you agree that this would still hold, right? So this would still hold, right? Now how do you get it? Natural log of both sides, right? That's minus the angle, right? So I'll put a minus sign over here. Then you got the angle that's half the distance. You'd have to double it to get the beam width. Follow me? Did that answer your question? Okay. So that's it. Do you have a question? Okay, you understand that or not? When I said natural log, this is what I mean. If I take the natural log of this and the natural log of that, now I get the natural log of 1/2 is equal to minus magnitude of the angle, right? All right, well, now I need to put a minus sign here. That's magnitude of the angle, right? That's in radians, so it'd be plus and minus that angle actually, right? Because that's an absolute value. Follow? Everyone? Okay. What next? You got a question? You look like you're looking.
I'm just waiting for someone to.
On this end,
Could you go over one of the per unit length DC resistances for wire?
DC?
Yes.
Well, DC is the easy one.
Could you go over both the DC and the AC?
All right, do you have a specific one in mind? Because if you have more than one wire, then they're all in parallel, aren't they?
Yeah, just,
I gave you
question was
props.
like 20 AWG.
All right, these are good because see, Wentworth's book is real basic, the way he addresses this. For single wire. Most of the time when you're dealing with AC resistance as a wire, you're dealing with bundles of wire. They're braided wire. You have a whole bunch. Now, you know, single strand wire is used in electrical connections, but it's stiff, right? It's used for fixed connections that don't bend. All the things that you use, like Cat5 cable and all that, where you plug in and they're moving, they're braided wire, aren't they? So braided wire doesn't have one wire, it has a whole bunch. It looks like this. When you talk about the AC resistance of that, you find the AC resistance of 1 and it's in parallel, so you divide by the number of wires. Does this make sense to everybody? To find the total AC resistance. And the reason they use braided wire in AC applications is because if you think about it, since the current runs on the surface, aren't we getting a lot more surface area if we braid wire? And if you take a whole piece of copper and make the equivalent amount of that copper in strands, you'll have a lot more circumference that way. And I'll show this to you later. I mean, you can figure it out. The area of those is pi a squared, right? The circumference would be n, the number of wires, right, times 2 pi a. Now, if I just said 2 pi a, small wires, is equal to 2 pi, call it cap a, which would be for large wire, you're going to find out that it's a lot more surface area when you have small wires, so that the total cross-sectional area is the same. You're going to have to trust me, and I'm not going to bother proving. Go ahead with the question.
Calculate the 30 unit length DC resistance.
It's AWG what?
20.
20 gauge?
Yes.
20 gauge, go ahead.
And then that's about what we
DC resistance?
DC resistance, it's in solid and
Oh, solid's easy.
32.
32 what?
19 times 32.
All right, 19 times 32 is 19 wires, 32 gauge. This is the one we can do solid first, right? So we'll do the solid wire, number 20 gauge. So just draw a picture of the cross section, and it has a radius A we're going to calculate, and it's got a conductivity sigma. I'm guessing the conductivity is 5 times, or 5.8 times 10 to the 7th, 1 over ohm meters, right? I think that's the conductivity they use.
And you get it to
Well, I mean, for copper, that's pretty standard. You all remember this for copper?
I think
So now it's solid wire, 20 gauge. Now you can look this up. You don't need to remember this, but I put that in there, right? What's the radius or diameter you're doing? Didn't I put a chart of that stuff?
I'm not sure if you put it up, but I found it to be 0.25 millimeters.
I thought I included that. If not, send me an email and I will. I thought I put in an AWG wire gauge thing.
There is one, it's not on that particular page, one like the beginning.
Yeah, in this section, for all this stuff. Anyway, so go ahead, give me the radius for this wire for solid.
I think it's 0.25 millimeters.
0.25 millimeters. Okay, so with that in mind, if we want the per unit length DC resistance, it's pretty straightforward. The only thing we can say, this is going to be our DC per unit length would be equal to, this is going to be per unit length, 1 over sigma, that's sigma, times the cross-sectional area, which would just be pi a squared, right? There's your sigma. You gave me A. Can you give me this, guys? You have your calculators and computers, right? So it rained once today.
Yeah, really are.
I'm gonna say it's gonna rain again, because all that's gonna evaporate. It's not even 3. Sigma 5.8 times 10 to the 7th, divide that into pi a squared, and A is 0.25 millimeters, 0.25 times 10 to the minus 3rd. And make sure you square it. You'd be surprised how many people make mistakes on this simple calculation. What'd you get?
That's square. Cubed it.
Went a little too far.
Again, 0.0878.
0.0878 ohms per meter. All right, so it's 87 milliohms per meter, 87.8 milliohms per meter, right? Agreed? Per meter. Now, let's find out what it is for this, only we'll do the AWG number 20, but now we'll go 19 by 32, right?
Yes, sir.
I'm gonna show you something else, guys. 19 by 32. That means it's 19 wires of 32 gauge. 32 is the gauge number. So go look up the radius for 32 gauge wire.
I don't think so. Oh, bingo. 624.
I got, so is it 32? I got 3.975
Maybe
3.975 millimeters.
Yeah. For 32.
That doesn't make sense. And I'll tell you why. This is less. Solid 20 has got less radius than braided 20, which makes
I'm
no
sorry,
sense.
did you say the diameter or the
Radius,
radius?
the radius, which one? 32?
32 gauge wire.
32.
It may not be in his book,
I mean, I found something.
but the one I put up there had it, I'm sure.
So the area of the
Just the area is pi r squared.
so the diameter of the 20 gauge wire, according to the book, is actually 31.96
Millimeters?
That's the diameter.
and that's
the diameter.
yeah, and that is millimeters or mil. So
Oh, mil is not, mil
yeah,
is not
no,
millimeters.
that's why the problem is okay.
Hey, mil is that's
45.4.
an English measurement. You gotta
Yeah.
take mil and turn it into millimeters.
Yeah.
A mil is what, 1,000th of an inch, right?
So
Yeah, a mil is 1,000th of an inch. You remember micrometers? You know what a micrometer is, a mic? Have you ever had to get the diameter of anything real small with a micrometer? You know what a micrometer is? It's a little device that looks like a question mark, and it's got a little thing that pushes up and down.
Mhm.
Down there, you measure it'll give you the diameter in mils usually.
Oh.
Mils are thousandths of an inch. All right, let's try it this way. Who has Google? Or whatever, or, you know, whatever, Yahoo.
0.2
For what?
gauge, 32 gauge millimeters.
Is 0.2?
To, yes, that's what this is.
Is 0.2 millimeters? All right, let's make sure. So
It's either 0.2 or 0.1, because I don't know if it's giving me the radius of its
well, it should say, just type in radius of 32 gauge AWG.
That's what I did, it's just quoted on the chart, but it doesn't sound right.
It says 31.96 mils, that's what we're looking at, right?
No.
No, it's a
You don't
millimeter.
want mils.
No, 2 millimeters.
Millimeter?
Yeah, it says it's 0.812 millimeters.
0.81, in radius or diameter? That's diameter.
That's,
Why don't you just look up radius, 32 gauge wire.
radius of 32 gauge wire.
And if it gives you mils, then change mils to millimeters.
Inches.
I'd say 0.1 for the radius.
0.1, we're gonna go with that.
Millimeters.
0.1 millimeters, great. What about over here for solid 20 gauge?
40 gauge.
Oh, there you go, 0.201.
0.405.
0.405 millimeters, we're gonna go. Okay?
That matches the
Back to this. What does this boil down to? You can see the fun we're having. I want to just show you guys that those solutions, I gave answers for these, right?
Yes.
The answers, but not like.
Not the steps. That's right. That's where you got to struggle. Believe it or not, you learn more struggle because you find out what you did wrong.
answer is 0.0335.
0.0.
335.
All right. So it's 33.5 milliohms per meter. This is per meter. So this is ohms per meter. All right. Back to this one. First, we calculate this. You said the radius is 0.1, right?
Yes, sir.
So that's 10 to the minus 4. Square that 10 to the minus 8, right? So it's really 1 over 5.8, isn't it? Because look, 5.8 times, or I'm sorry, it's going to be 1 over 0.58. So it's 2 about, right? You go ahead and do this and just check. Do you agree with me? Take a look at this. So this radius is 0.1 millimeters. That's 10 to the minus 4th, correct? Meters. Square that, you get 10 to the minus 8. Multiply it by sigma, you get 5.8 times 10 to the minus 1, right? That's 0.58, isn't it? Take 1 over 0.58, what do you get? Anybody?
What I'm getting is 1.72.
1.72 ohms. Now divide that by 19.
0.09.
Huh?
0.09.
Yep.
1. 0.091.
Ohms, right?
Yes.
That's what it is for 19 by 32. This is DC. Here's what it is for RDC for a solid AWG20. You with me on this? It's early today.
Actually, it's around 10.
Oh, I guess you're right. I thought it was 9:15 the other day, or 2:15 it went off.
That was late.
Anyway, I don't know.
It's no.
Yeah, I mean, what does the answer in the book say?
It doesn't give
I mean-
one for the AC, but for the
I mean, DC.
DC, it's
This is DC, right?
Yes.
1.31 milliamps per meter
For which one?
for the number 20 gauge.
Solid?
Solid.
What was the value?
1.31 million pounds per meter.
Is the one on top AC?
No. This is the resistance for one strand. All right? If you have 19 strands in parallel, you divide by 19, right? Just think, if you have two resistors in parallel, you take one, at the same value, take value of 1 divided by 2. 3, the value of 1 divided by 3. 4 and so forth, you divide by the number. You got 19 in parallel, right? So now forget that one. The solid one is what we calculated earlier, right? For the solid one, what do they have?
They have 1.31 million per meter.
Then something is amiss. And that means that radius there, this is millimeters, isn't it?
Yes.
Is that right?
According to the table. and
Radius.
Yes.
Not in mils.
Yes. That is radius in millimeters.
There's something wacky here. I mean, I do these things
Yeah.
when I teach EMC.
So this is how I did it.
No, I want to see the problem.
Oh, okay.
So that was the one that I was talking about.
That's number 6 gauge.
No, the first one was 6 gauge. I was just curious about that one.
All right,
And then,
so that's the second one. Hold on.
and so that's, this is second.
First, second is 1.34 milliohms. Right?
Yeah. 1.1.
Oh, no, it's the third. The first one is number 6.
Mhm. So,
But look, AWG solid and braided. So then the third ones are 20. So 1, 2, 3, there we go.
33.
That's exactly what we got.
Okay.
Yeah, we got the right answer.
Sorry.
You gotta read the answers right. So that's what it is for solid. And for braided, check the next answer. What is it for braided?
28 million.
Let me see that.
I'm just reading the one.
Which ones are right?
Oh, the first one we did the solid one, left side.
The 0.033.
Yeah. One that wire.
What was the
Did we do
answer?
that?
The second one?
28.
What chapter is this?
It's not, that's what we said.
Which homework?
The very last one.
I was like, I like that equation. That's pretty.
Wait a second, is that radius for, right, for 0.1 millimeters for number 20, or for 32 gauge wire?
Yes.
I got 0.2, but it didn't really change much.
This says the diameter. So,
Should have any point.
millimeters.
I'm not doing it.
Yeah, are you sure?
I don't think that's what it is.
Okay,
This is.
gauge diameter, so you gotta divide by 2, keep going down to 32.
Yeah, actually.
I got the 32 gauge.
Does that?
Yeah.
But I plugged it
All
back.
you did-
And then you divide by 2.
So just go.
You gotta.
It doesn't get through a
The
point wire.
Oh, yeah.
Oh, that's all.
Yeah. So yeah.
So is that resistance right?
Is there a
1.7?
reason you don't have a pi for calculating that resistance?
Where?
R32 gauge.
No, you need a pi. That's because I erased it. I was messing. This should have the graphs there. This should be pi a squared. I'm so glad you saw it. Yes, that was because I erased it. I had it down there. I erased it. This should be pi a squared. Divide this by pi. Actually, just divide this by pi.
Yeah, final answer 0.0289.
Yes.
Yeah.
Yeah,
Okay.
just goes to show you can make mistakes. I mean, you can't read right, and then you can't calculate because you got the wrong form. Anyway, yeah, it works out every time. Now, for AC resistance, this is my point. If you do AC resistance, you're going to find out the higher the frequency, the braid will be less. All right. If you look at the actual cross-sectional area of the wire, it's the same. All right? I mean, when I say that, the actual diameter of the braided wire bundle is the same as the diameter of AWG 20 solid. Are you with me? And that's real important, because when you get AWG wires, it's the American wire gauge. Do you know how they calculate gauge? Who here has fired a shotgun? You know, 12 gauge, 10 gauge, 20 gauge?
Yeah.
It's an old English system. If you put a circle down right there, and it had I think it's 0 gauge actually. How many balls can you put in there where they're all next to each other without, falling out? In other words, with no gaps between them. The number of balls has to do with the gauge. So 20 gauge shotgun is that big, right? 10 gauge is much bigger. You can only get 10. And if you get 8 gauge, it's like a cannon. Now, it's the same with wires. There's a standard gauge, 1 gauge, where you can put 1 wire through. And then like 4 gauge, you can put 4 wires in there and they'll be snug up against each other. Then that's how they get gauge. It's an old English measure. What are you going to say?
I was gonna say, how big are the balls, the standard? Like,
You want to know where most of this happens? Where it comes from? It comes from back in the ancient days when they had to measure out stuff. They found some measurement that was everybody had access to. And I don't know what it was for this, but it was like a hoop or something that was a standard thing, and they used it. By the way, you know how come railroad tracks have a certain width? That goes back to the Roman days, believe it or not, from what I've been told. And it has to do with the width of wagon wheels used for the chariot. I'm not kidding. This stuff goes way back. Anyway, Gross has got it. If you talk to Dr. Charlie Gross, he can give you a history on where the term acre came from. It's the amount of ground a mule can plow in one day. That's what an acre, how it was meant. I'm not kidding about this either, which is bizarre to me, but it's true. But that makes sense in a lot of ways, that things that are common, that people are exposed to, are used for measurements. There's one word that's translated out of the Bible, cubits. That's how it's translated in English. I looked into this. Cubit measurement is the distance from your elbow to the tip of your hand. So it's actually about 18 inches for most people. I didn't know that. It was fairly standard. All these things come from something that's common. What other things? Sorry about that. If you wanted the AC, you would have to calculate the AC resistance of one wire and then put them in parallel, divide by the number. And I would never expect you to know the conductivity of copper or the American wire gauge diameters or radiuses. I would give you that information. So don't send me emails about this. Yes?
I would like to make the same, that was from chapter 9. Will it be elements of chapter 9 on the test right there?
For AC resistance? Well, we did cover some of that with skin depth, didn't we?
Yes.
Yeah, why? Make sure that you understand. Right. Just because, yes, it's fair game. We covered skin depth, we covered AC resistance. Remember?
Sure.
Yeah.
Elements from,
but we
the
didn't.
homework is from chapter 9, so I was wondering.
Yeah, what I'm trying to do is, that homework that I gave you there, you should be able to handle it without any problem. Okay. Are you going to see it? I don't know. It doesn't seem difficult. It seems like a gimme, but by the same token, I'm not sitting where you are. So back to the problems. Let's go through some more. Nothing? What about like with radar, got a radar signal, it's coming out of an antenna, it's hitting another antenna. Maybe not radar, transmitter signal with a receiver, and I've got a weird load on it, and I want to calculate the power dissipated.
I don't have a problem, but
waveguides too, right?
Huh?
We haven't talked about waveguides in a while, right?
Yeah, but I was trying to figure out how on a receiving antenna, how do you find is it P load? Is it power across that load?
Power dissipated at the load, yeah.
Is that different from power received?
Yes, remember that? Quite different, right?
Okay. P
received is theoretical. P dissipated or P load is the actual power. We can do one. By the way, the test is cumulative, so it's from chapter 6 through into chapter 8, right?
Yeah.
All right, so we've just, before we get down that road, we've covered propagating waves, waves reflecting, we've covered shields, remember? Got something that thick and you want to know how much power gets through it. We've covered reflection coefficients, right? We've covered oblique incidence, even though if anything I ask you about oblique incidence, I'll provide the formula. You'll have to select either parallel or perpendicular polarization. Remember that from chapter 6?
Oh.
Right? And then we've covered waveguides. There's TE, TM modes. We've covered antennas, radar. We've covered the Friis equation. I'm trying to think of all the other things. There's other things.
Arrays.
Huh?
Arrays.
Sure. It's just a lot of this stuff kind of overlaps in certain senses. But, I mean, you could say chapter 6 is included in chapter 8 because it's propagating waves. Yeah. But in chapter 6, what did we do? We actually solved the del squared equation. We solved 2 curl equations and we got a single equation and solved that for a plane wave, right? So we actually solved the differential equation, then we applied it to different constitutive parameters to get the intrinsic impedance and beta and all that stuff, and velocity, propagation. Now to your problem. And I really think that a lot of people miss this. So Isaac, right? What Isaac asked was something. I'll try to learn your names. I know Jacobs because I get email from him all the time. And I'll try to learn the rest of yours. You just have to bear with me. So here we have an antenna with a given transmitter gain, GT. It can be a function of angle. Then we've got some radial distance R. We've got a second antenna with a receiver gain. And I'm going to put a load on this thing, a theoretical load. I'm going to just call it Z load. And what I'm after just the current, I load. Now, if I want the power, then I'd take the real portion of Z load, and then I'd say it's 1/2 I load magnitude squared times Z load, right? How many times the real part of Z load, and I will get there. So how do you solve this problem? We usually we assume the transmitter power, but you can do this in an inverse problem. I can say this is that much current, how much power was transmitted, right? Either way is acceptable. So you have to be familiar with the entirety of how to do it. So I'm going to start here. I'm going to say there's a certain transmitted power. If I put down a number, you might like it better, but just a certain transmitted power. So the next thing I do, I like doing it this way. I like saying, what is the average power density right here? And here, the average power density, this is going to be the power density at this point. We could get the electric field strength, and I may ask this, by the way. You should know how to get the electric field strength there, if it's air, right? But the power density would be transmitted power times gain in transmitter. And that may be a function of angle over 4 pi r squared. And that is in watts per meter squared, right? That's the impingent power density. Now to get the power received, and this is theoretical. It isn't actually the power received, is it? This is only a theoretical constraint. It's the maximum power received. And even if all of it's received, half of it is re-radiated anyway. So this P received is going to be P average times the aperture of the antenna. And the aperture in the antenna is the electrical size, and that's lambda squared over 4 pi times the gain of the receiver. Y'all remember that? Now, Friis equation comes out of that. I like to do it this way, because that way, anything I want, you've got. You can, if you've got the average power density, you've got the electric field at this point. That's equal to 1/2 magnitude of the E field squared over A0 at that point, right? You can calculate the electric field. A0 is 120 pi ohms, right? You can get the H field if you got the E field. Divide by A0. In other words, there's nothing you don't know. So this is the average power. I mean, this is the P received. If you want to, you can put the whole 9 yards in here. You can put P transmitter over 4 pi. Then you can put R squared right there times gain transmitter, then times lambda squared gain receiver over 4 pi. And lo and behold, when you do the whole 9 yards, it's transmitter power. And then it's going to be times lambda over 4 pi R squared, right? Times gain transmitter, gain receiver. And that would be a form of the Friese equation. Right? And if gain is the same, you can put gain in here. But I'm doing it to make sure you see. Y'all with me on this? Okay, that's P received. But remember, P received has to do with the maximum theoretical power. And that theoretical power, right, we found was equal to what? Do you remember this? Well, remember where I drew Z antenna and then I had Z load had to be the conjugate of that? So only the R mattered. So the real part of the antenna impedance. So that was equal to what? It was 1/2 times I squared. I mean, now actually we used V, didn't we? VOC, right? We do it with VOC, right? Squared divided by the resistance, which was 2R antenna or R rad, right? Remember that? Right, why 2 rad? Because you got radiation resistance of the antenna and the load resistance is assumed to have an identical value. And the imaginary components go away because you're gonna have a conjugate for the load impedance.
So if you just say like Z load and you don't give us a value for it, we should assume.
What's that?
If you don't give us like a direct value for Z load, we should just assume that it's the direct conjugate.
No, I mean, to calculate P received, you always assume it's ideal because this is a theoretical. It's not a real, it's not something you're going to observe. This is the maximum possible. If it's an open circuit, we get none of this, but still the value that we used to get the open circuit. So now that means V open circuit right here, right, is equal to the square root of 4 times P received times R rad. Now that is something that's observable and measurable. And if you take an antenna and you cut off the load and you were to measure just the open circuit voltage, you'll measure that. But remember, there's no power being received until current's drawn. If there's no current, there's no power. There's an open circuit voltage that it is observable. Okay? Y'all with me on that? Open circuit is like go to a wall voltage and measure with a meter. No current theoretically drawn, but you'll measure about 117 volts RMS, or you'll measure a peak voltage about 160, 170, somewhere in there. And it doesn't matter. The thing about it is until you put a load in there that draws current, you don't have any power dissipating. So P received is used to calculate that. That's observable. Now, when you have the open circuit, now you use that voltage plus the minus VOC, which is there, and now you put the load on. But I got to tell you this. Remember that antenna impedance is still there. You all with me on this? So you still need to put the actual Z antenna here. And Z antenna, right, has equal to R rad, the radiation resistance, plus JX antenna here. So it's got to have Z antenna, then you put ZL. And then to calculate this current I, you would take this divided by the 2.
So if for example, it's a half wave, that Z antenna would just be your 73.2 plus.
73.2 plus J 42.5.
Okay.
You got to add the J, unless I say it's cut down to 0.485 lambda.
But that's, okay, yes, sure.
Another thing you guys should know, I expect you to know the 73.2 ohms. And remember, we covered monopole too, right?
Just have that.
Monopole, yeah, that's right. And directivity doubles, resistance is half. I'll give you I'll give you the radiation resistance for short dipole, the formulas for short dipole loop antenna. I'll give you that. The gain you got to know. Anything that's short or small, it's 1.5 sine squared of theta. Okay, you need to know that. For the half-wave dipole, I'll give you the gain of that. The 1.64 times the cosine of pi over 2 cosine theta over sine theta, because you guys might mess that up, and that's understandable. I mean, the basic equations you should know, like the stuff we're going over right there. Okay, so that's how you would do it, and then for I, you would calculate VOC over Z antenna plus ZL, correct? Once you had that, if you wanted power dissipated at the load, the real power, then you take the real value of ZL, multiply it by I squared, IL squared, and divide by 2, right? Because this is still AC.
I'm sorry, that's solved for what?
Real power. You see, if that's ZL, it could have a real and imaginary part, right? If it's just the inductor, say it's got J10 ohms, no real average power is being dissipated. Follow me? So to get real average power, if, for instance, I here, I think you all agree with me, would be VOC divided by Z antenna, whatever it is, plus ZL. Correct, guys?
Mhm.
Now, the power dissipated by the load, this is power at the load, and it's average power, right? That would be equal to 1/2 the magnitude of that current I squared, and then it would be times the real part of ZL. Because the imaginary part doesn't dissipate power, just the real part. Okay? What else? It's a good question. You all have access to these videos, don't you? I haven't looked at these in a long time. I mean, it never hurts to go back. At one time, I think the bigger the class, the more, especially with Zoom, when a lot of people were coming, you got more questions about the video because people didn't watch it live. What they did is watch the video, so the kids are just emailing, well, what about this thing? And I regret it. Oh, if I only put time markers in these videos or something, because I don't know what happened, 15, 20.
Lecture number 10. What day is lecture 10? I don't know. Yeah.
You know, this is a very good class. I just want to tell you. You're very responsive. I can tell you there's a lot of interaction. You guys are keeping up. You're generally inquisitive. I take classes. We're as close to death as possible with my students. I mean, they didn't want to be there. They were there. They could care less about the subject. And I just want to tell them, it's like, look, if you don't like engineering, there are other careers, right? You don't have to have a gun to your head. You will not be shot to death for not doing this. But I don't know. I mean, I've always thought if you're in college, I paid a lot of my way. You should really want it and try your best. Don't do this like you did, high school history or something. Gosh, I had a bad attitude in high school. I hated writing English papers. I could care less about, that time, Shakespeare. But the only guy I cared about was Hemingway, because you were an old man to see. I don't know if you were there. I mean, I really didn't appreciate my education. I should have more. I regret that. Love math and science. What else? Surely there's got to be something with waveguides or something with, nothing.
You're feeling generous, you got any hints for specific things to study?
I haven't made it. Yeah, I mean, for sure, make sure you know propagating wave theory, right? When in different media, the attenuation constant, you know how to calculate wavelength, right? Remember all those things? Wavelength, beta. Let me just do this because this has been a while. Way back in Genesis 1, God said, let there be light, and the curl of E was, gosh, this is not meant to be in any way bad. Minus the BDT and curl of H. I just think, that I'm talking in there. You can get scissors. Anyway, that's Maxwell's equations. Sort of, they dictate photon behavior, as we know. Anyway. So from those, we went to the time domain, or frequency domain, right? And then we got one equation. Now, I'm just going to say, when that happened, this becomes minus j omega mu times h. And this becomes what? Sigma plus j omega epsilon times E. If you remember when we did that, right? Then we turn the crank on this one. We got one equation with one unknown, and we set the divergence of E equal to 0, and that's rho V was 0, right? And then after that, we got one equation with one unknown. It was this crazy thing. We had del squared of E, right? Minus gamma squared of E equals 0, and gamma, I don't have time to go through all of it. Gamma was equal to the square root of j omega mu times sigma plus j omega epsilon, and gamma was equal to alpha plus j beta. Go with me? Now, something to be said about this. I jumped from there to there, but once you got these two equations, you just take another curl of this one, and then you replace the curl of h with that, and then you condense it down, and then you use the vector identity and the curl of E. And I'll just, this is the kicker that gives it away. That's the thing you need to get down to that equation. All right. Do you remember doing this sort? We did it, and it's done. I think I did it at least twice. It's something that if you're an electrical engineer, at some point somebody's going to say, "Hey, remember how to do this?" In some way, shape, or form, they're going to bring it up, and you're going to probably go, kind of, because he's a physicist probably, and physicists live in this world. They know this like we do V equals IR. So now it comes down to this point, then we made all sorts of assumptions. We assumed what? We assumed we have plane waves, right? And the waves were only varying with Z, and they only had an X component, right? So when we solved this equation, I don't have time to go into this, but this became just a double derivative of EX with respect to Z squared, right? Second derivative of Z. And then we found out when we got the second derivative of EX with respect to Z squared, right there, minus gamma squared EX equals 0. EX, lo and behold, had EX0 plus e to the minus gamma Z plus EX0 minus e to the gamma Z. And this is a right going, this is a left going or reverse traveling wave. Do you all remember that? We did this, and then we found a few other things. Now, I'm going to cut to the chase on this one because now I'm over by 20 seconds. The things that we found that were critical were velocity and beta. Beta is right here, right? And we know that gamma was equal to alpha plus j beta. So if we only worry about the right traveling wave, we have E equal to some EX0, e to the minus alpha Z, which will give us our skin depth, times e to the minus j beta Z. There's beta, right? And we can get the velocity, phase velocity we found as omega over beta. Do y'all remember that? Remember I said for a very good conductor, it's much, 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 much less than the speed of light, right? Down to thousands of meters per second, something that's, you could fire a bullet faster than that. So it becomes something unintuitive. That's the phase velocity of the wave. And what is the wavelength always? Well, that's assuming the speed of light.
crossway.
In general, the way you get, what does it say again? You know this, right? Wavelength is 2 pi over beta. Jacob said it right, because beta is radians per meter, right? So wavelength times beta have to be 2 pi. It's a full 360 degrees or 2 pi radians. That's how you get it. You always use beta. And remember, beta can be a lot different than what it would be if it's free space. Just remember those things. Now, if it is free space, the nice thing is this equation. If it is free space, so beta of air, you might say, is just omega squared mu naught epsilon, or omega over c. All right, I'll stick around as long as you want me to. Or you want to email me questions, it's fine too. Hope you don't get caught in the rain. I've been in this, I've taught you guys several times rapid rain here. Well, one time we had a Senate meeting, and it was like a major rainstorm, thunderstorm hit, and you could